Welcome everyone to this webinar hosted by the Institute of Navigation titled WAAS in the Ionosphere, a Historical Perspective Monitoring Storms, published in the spring 2022 issue of Navigation, the Journal of the Institute of Navigation. This paper and many more are available at Navigation's new open access portal, which is available at navi.ion.org. You can check it out. There you can read, download, cite, and share this article and many others. Today's webinar is being presented by one of the paper's authors, Dr. Lawrence Sparks. Dr. Sparks is a member of the Ionospheric and Atmospheric Remote Sensing Group in the Tracking Systems and Applications section at NASA's Jet Propulsion Laboratory. He received his PhD in Applied Physics from Cornell University and has pursued research in various fields, including fusion plasma physics, solar magnetohydrodynamics, atmospheric radiative transfer, and ionospheric remote sensing. He is a member of the WAAS Integrity and Performance Panel and is currently working on issues concerning the impact of the ionosphere on satellite-based augmentation systems. Following his presentation, we'll take questions. You can ask a question at any time by clicking on the Q&A box in your viewer. So thank you for being here, and now we'll turn it over to Dr. Sparks.
Thank you, Rick. I want to thank Navigation for giving me this opportunity to present material that I and my co-authors have been involved in for the last 20 years now. And I do want to acknowledge my co-authors, Eric Altschuler, Nitin Panya, Juan Blanc, and Todd Walter. As we've been involved with work benefiting the Federal Aviation Administration's wide area augmentation system. That's what WAAS stands for, or what the acronym stands for. As many of you probably know, it's a satellite-based augmentation system which is designed to make GPS safe and reliable for aircraft navigation. WAAS was commissioned on July 10th, 2003. And I'm going to be discussing basically the history of the impact of the ionosphere since that time on WAAS. This is actually the first of two companion papers on the history of WAAS over 20 years now, or almost 20 years, on threats posed by the ionosphere to accuracy and integrity. And this paper, as the title indicates, is focused on the impact of ionospheric storms, which are very large-scale events that disturb the ionosphere. The second paper is going to be addressing the impact of smaller mesoscale irregularities on the ionospheric threat model that are not nearly so necessarily so widespread. Our two papers may be regarded as supplementing the broad review of the improvements to the WAAS service and integrity since 2003. That two of my co-authors authored that paper as well, and it was entitled WAAS at 15. So if you're interested in other aspects of WAAS over this period, that's a good paper to consult. I'd like to begin by dedicating this presentation to the memory of one of our co-authors, Dr. Nitin Panya, who I regret to say died in this spring. He was a wonderful colleague. I interacted with him on several papers, and he will be very much missed. Okay, the objectives of this paper are fourfold. I wanted to describe how WAAS monitors the state of the ionosphere. I want to highlight the integrity and availability concerns that have led to the development of the irregularity in storm detectors that are in WAAS. I'm going to report on the algorithms that define these detectors and how they've evolved over the existence of WAAS since 2003. And we'll conclude with examining a scalar metric that's used to scale, to rank the magnitudes of the largest storms that have occurred over the past two solar cycles. Okay, and there is another goal, actually, objective that I haven't listed here, and that is, this is essentially a review paper of material that's been published previously almost entirely in conference proceedings. I'm not aware of much of anything that I'm going to be talking about today that's actually appeared in a refereed journal article. But so one of my goals, or well, one of our goals, I should say, in writing this paper has been to provide an extensive bibliography that provides access to the many conference proceedings that have contributed to this work. Okay, the outline of my presentation. I'm first going to give a brief introduction to WAAS for those who may not be familiar with it. It'll go very quickly. I'm going to discuss the methodology for monitoring the ionospheric state that WAAS uses, and this will focus on two aspects of it: how ionospheric delay estimation is performed, and the disturbance metrics that WAAS uses. And then that will lead into discussion of the extreme storm detector that was implemented in 2007. And then subsequently, a few years later, we implemented a moderate storm detector. I'll discuss that, and I'll conclude with the storm ranking that I just mentioned. Okay. Satellite-based augmentation systems in general have the goal of improving the accuracy, availability, continuity, and integrity of satellite-based augmentation of global navigation satellite systems. And GPS, for example, generally performs very well in these categories, but when safety of life is at stake, the specs that GPS meets with regard to these categories is not adequate, and it must be supplemented by some sort of satellite or some sort of augmentation system. Integrity here refers basically, if you're not familiar with that term, it refers to the fact that the position estimates that are determined from the system can be trusted. Now, this is, I like to present the following photo of the airport in Juneau, just to show you that there are certainly places where the ability to use WAAS safely is very important. As you can see, if there's poor visibility, a serious problem could arise if the pilot doesn't know exactly or within certain bounds where the plane or the aircraft that he's navigating is located. And I would just like to say also peripherally that I've had the pleasure over the years to occasionally talk to pilots who fly in Alaska. And I think of all of our customers, the pilots in Alaska are the most appreciative of WAAS. I think it's made a huge difference in their life. Okay, next slide. Okay. This slide presents the configuration of WAAS receiver stations that was in place when WAAS was commissioned in 2003. There were 25 stations in US, Canada, and Mexico. Each WAAS receiver station has 3 dual frequency receivers. These receivers transmit data or information about signals emitted by the GPS satellite. They transmit these data to wide area master stations. And these master stations determine differential satellite corrections, geosynchronous Earth orbit parameters, ionospheric delay corrections, and integrity confidence bounds. In the number of stations in the network were augmented first in 2006 when 4 stations in Alaska were added. Then in 2007, 3 additional Mexican and 2 Canadian stations were added. And finally, the final addition was made in 2008 when 2 more Mexican stations and 2 Canadian stations were added, leading to a grand total of 38 stations, which is the configuration that we enjoy at the moment. Now, what does WAAS do? Among other things, it defines a grid where basically this grid defines the region that WAAS provides its service, and on this grid is, at least at the lower latitudes, is a 5 by 5 degree grid, and at each of the grid points, WAAS broadcasts 2 parameters. I will refer to the grid points as ionospheric grid as IGPs, which stands for ionospheric grid point. The 2 parameters are the ionospheric grid delay, which is an estimate of the vertical delay that a radio signal experiences as it propagates vertically at that location. And then the second parameter, which is arguably even more important, is the grid ionospheric vertical error, which is a safety critical confidence bound on the error in the delay estimate. And this is used to help determine error bounds on the position estimate that the pilot computes on his aircraft. And so anyway, so WAAS is basically providing corrections to position estimates and with a very high degree of reliability. Okay, the methodology WAAS uses employs what's called the thin shell model of the ionosphere. I'm always astonished that this very crude model of the ionosphere works so well under nominal conditions. Very simply, the model assumes that all the electrons in the ionosphere are collapsed into a single shell of infinitesimal thickness at an altitude of 350 kilometers. And under quiet or nominal ionospheric conditions at mid-latitude over North America, the spatial variation of the vertical ionospheric delay has been found to be very well modeled locally by such a plane. This model serves two very useful purposes. For one, it associates an ionospheric pierce point, or where the ray path of a measurement intersects the plane, that is we refer to as an ionospheric pierce point, and so it has a single pierce point associated with each ray path. And then the other useful thing it does is that it allows an estimate of the vertical delay at that pierce point to be determined simply by multiplying by a geometrical factor depending on the elevation angle. And that greatly simplifies the analysis. And so to actually compute the quantities that the system broadcasts, I'm not actually going to go into the algorithm. My time does not permit me to go into the full algorithms. Basically, the idea is that an estimate of the ionospheric delay can be achieved by a summation over a weighted sum of various measurements that have been converted to vertical delay, and the weighting factors are determined by minimizing the estimation variance subject to the constraint that the estimator be unbiased. Now, the initial operating capability of WAAS used what we call a planar fit algorithm that assumed that the vertical delay estimates were all uncorrelated, which and then later in 2011, we introduced an alternative algorithm, which was actually a more general, of which the previous algorithm was a special case, where the vertical delay estimates were assumed to be correlated. The algorithm is known in the business as a Kriging algorithm, and it originated basically in South Africa back in the 50s. And it's proven to be a very useful improvement in the WAAS estimation scheme. The paper that I'm reporting on reviews the estimation methodology, both of these in much greater detail. And so I'll refer you to that paper if you're interested in that. The give quantity that I mentioned, the grid ionospheric vertical error, is computed as a constant times this quantity called sigma give, which is defined, the square of which is defined to be this, essentially, this is a little simplifying it, but essentially the sum of two terms, one of which is related to the formal error that is derived from the fits that are used to estimate the vertical delay at, that are used to measure the vertical delay. And we have to supplement the formal error. It's actually inflated to be conservative, but the formal error gets supplemented by another quantity, which we refer to as sigma undersampled, that is implemented to protect the user from the effects of undersampling the region that you're interested in. Okay, so let me go show you how that fit is performed. Here's an example of basically the same technique is used whether we're computing ionospheric grid delays or vertical estimates of vertical delay at the IGPs, where in this case we pick out a particular grid point that we're interested in getting an estimate at that value. We collect all the measurements that have IPPs near the fit. And typically it's 30 IPPs are sufficient, and this circle starts out at 800 kilometers. And if we don't have 30 grid points or 30 IPPs within the circle, we expand the circle until we get 30, or up to a limiting value 2,100 kilometers for the fit radius, and then at that point we live with what we have if it's deemed sufficient. And then another quantity that we keep track of is the radius of the radius vector for the to the centroid of the distribution of the pierce points that go into the fit. And these okay, I should say first of all that the chi-squared of the fit is a very useful quantity in WAAS. It serves basically to detect disturbances. It's been found that actually that there's a strong correlation between the presence of disturbances in and around this fit domain and ionospheric disturbances from whatever cause, and the value of the chi-squared of the fit. And so the chi-squared is the basis of what we refer to as the irregularity detector. When the detector trips when a disturbance, when the disturbance metric based on chi-squared exceeds the specified threshold, and when that happens, the broadcast parameters, the IGDs and the gives, are not available for use by a pilot. Okay, let's. Oh, and then I also want to highlight what's called we call the threat domain of the IGP. The threat domain is basically the region where of all the points that are closer to a given IGP than they are to any other IGP on the grid, and that defines the threat domain. We do use estimates of the vertical delay at points within the threat domain when we're tabulating the ionospheric threat model, which I will be describing in a moment. Okay, let's see. Okay, I first wanted to define what I mean by a threat. This is the formal definition of ionospheric threat in the WAAS system. Whenever the numerator here represents the fit residual between an estimate and its true value, and then a threat occurs when the fit residual is sufficiently large that this inequality is satisfied. In other words, when this inequality is positive. And essentially what this means is we want a Gaussian distribution with a standard deviation that corresponds to this sigma kappa, which represents more or less the formal error of the estimated vertical delay at the point in question. We want that to be a Gaussian distribution with such a standard deviation to bound the distribution of fit residuals out to a distance of k, which is in this case 5.33 times the sigma, which is used as standard deviation. So anytime that we have basically anytime that this inequality holds, we have a threat present. Now these threats are tabulated in I'll just show you an example of the threat model here. I'll discuss it more or a little more brief later in the talk. But we tabulate the threats that I just defined as a function of the two IPP distribution parameters, the fit radius and the relative centroid metric. Well, actually, it's labeled relative centroid here, but it's actually, this axis is actually the ratio of the centroid, the length of the centroid metric to the fit ratio. And then this table is basically a lookup table that once in a new situation, when you have you're given a fit radius and a RCM for a fit, and you're trying to compute the vertical delay, the sigma squared that appears in the sigma undersampled squared that appears in the give expression is derived from this table. Okay, well, let's put this all together now. Let's see, where are we? Okay, here I've prepared an animation here that just shows you how a pilot, how the system works from the point of view of the pilot. Initially, of course, these GPS satellites are all emitting radio signals at their assigned frequencies. We work from the grid that I mentioned that's situated at 350 kilometers. The first thing we do is to identify all the pierce points of the signals that are going through that grid. We then compute we use the thin shell model to compute an estimate of the vertical delay by doing that multiplication with the geometric factors. So we have at each grid point an estimate of the vertical delay, and then we have define a point at which we want to get an estimate, and we select just the vertical delays that are the estimated vertical delay, or the vertical ray paths that are in that, or the IPPs, I should say, that are in that fit domain. And then we perform the fit, and that gives us an estimate of the vertical delay at the grid point. We repeat this process at other relevant neighboring grid points. And then when a plane comes in and has a grid point that pierces in the middle of a cell that has where we've defined the four vertical delay estimates, an interpolation is performed that gives, let's see what happens here. Okay, wait, I skipped a little ahead there. So the interpolation gives the estimate of the vertical delay at the plane's pierce point, or I should say the pierce point of the signal that's going from the satellite to the plane. And then the slant to vertical, in this case, the vertical to slant conversion is performed to get an estimate of the slant delay that's affecting that signal. So that's I should add that this correction can be used so long as the disturbance detector based on chi-squared of the well, in this case 4 fits, as long as they haven't tripped, or at least most if they haven't tripped, let's put it that way, he's free to use this in his to correct for ionospheric delay. Okay, so what can go wrong? What can go wrong is that the space weather can present a threat to system safety. A storm can be generated by coronal mass ejections. This is just a typical coronal mass ejection. If the trajectory of the mass ejection hits Earth, and this will cause a GNS signal to experience an unusually large ionospheric delays. Of particular concern are compact mesoscale irregularities that have been observed to arise following extreme storms. These can escape detection if they're sufficiently small, and they are potentially a major source of positioning error. Under extreme storm conditions, it then becomes necessary to deny the use of the precision approach service. And I want to give you an example of a very important example of just such a storm that produced these kinds of compact irregularities. The famous, if you've studied the ionosphere, you'll be very familiar with the Halloween storm that occurred. It was actually the result of 2 X-class solar flares that generated coronal mass ejections that arrived on successive days. So in a sense, it was 2 storms back to back. But the storm produced large increases in ionospheric delay during the day. But then what was really of concern was what happened at night. The compact regions of high electron density that were found to persist into several hours into the night. And this was unusual because under normal circumstances, the recombination occurs in the ionosphere and basically all the irregularities more or less disappear, and there's not much going on at night. So it was very unusual to have a region of high electron density persist for many hours into the night. And in fact, this highlighted the need to revise our WAAS methodology. This represented a very serious potential problem to the system. And I want to illustrate this by, if you look at the figure on the left, this was generated using data from the CORS, what's referred to as the CORS network, which stands for Continuously Operating Reference Stations. And at the time of these data were recorded, there were something like 1,100 stations in the network. So you could really map out what was going on very thoroughly. And what I want to focus on is this region over Florida and southern Georgia, where a very localized irregularity occurred. And this, if the system had not detected this irregularity, it could have led to very serious positioning errors, and it's fortunate that the system did in fact detect it, but one of my co-authors, Todd Walter, I think, or at least he or some of his colleagues, prepared this figure several years ago that shows in a little more detail the irregularity that occurred and this is several hours into the night, I believe. And just to emphasize the point, Todd actually, or whoever prepared this figure, removed the points that there were 5 points that actually did sample the irregularity, and they've been removed just to show you that well, how an irregularity might go undetected. And in fact, if you look at if you imagine, here's the irregularity. If you imagine it moved, if it had been a little bit to the southwest, it actually could have fit between the points that were sampling it. So it's not out of the question that had it been in a slightly different location, it could have gone undetected. It was later learned that a non-negligible fraction of the charged particle density was above 700 kilometers. So this is a very much higher in the atmosphere than one would normally expect to see such phenomena. And of course, you wouldn't really expect to see it at all at night. And the peak of the density profile is, it was found to be in the vicinity of 500 kilometers. And I want to emphasize, however, that the local disturbance detectors based on the chi-squared metric that I talked about previously, they did in fact reveal the presence of this irregularity, and so the system responded appropriately, and no what we call HMI was broadcast. HMI is an acronym for hazardously misleading information. And so, so we were okay, but we kind of lucked out. Had the Florida event gone undetected, the initial ionospheric threat model would have been insufficient to protect the user from errors or from positioning errors arising from GPS signals that intersected this irregularity on their way to the user. So we were kind of lucky, but but this really actually focused us on a lot of activity for a good couple of years on how to deal with this situation. And it, just to be sure that this wasn't just an isolated case, we subsequently looked at the other largest storms that occurred in the solar cycle 23 and found evidence that the similar compact irregularities occurred pretty much in all the major storms. The only, if you look closely, it's kind of hard to see this figure, but if you look closely, you can see evidence of big irregularities in these 4 storms. This one, not so much so. This one, you really don't see much of anything, but this is the storm that occurred on April 1st, 2001, was actually much smaller in magnitude. And in some sense, it really is a moderate storm, but because of the way we set our parameters, we've set our parameters very conservatively to define even at the upper edge of moderate storm level. We're going to call that an extreme storm as far as the operation of the system is concerned, just to be for the interest, in the interest of safety. Okay, so let's go on to the next slide. All right, so what this led us, the drawbacks to the initial way we approached this problem. Initially, we had all these threats were incorporated into the threat model in the tabulation of threats that I described earlier. And this effectively assumed that the worst threats ever observed are always present. This proved to be unsatisfactory. On one hand, it was overly conservative because it meant that this actually limited availability. But at the same time, it wasn't entirely safe because it didn't allow for the possibility that you could have worse threats occur in the future that the threat model wasn't prepared to handle. So the solution was to introduce an extreme storm detector. And let's see, here we go. Okay, and the storm detector is like all of our measures of ionospheric disturbance are basically related to the local disturbance metric that I talked about earlier, that's proportional to the chi-squared of the fits at each of the IGPs. This is obviously a function of space and time. It depends on where you are on the grid. And when The irregularity trips, I think I already mentioned that the broadcast parameters are not available for positioning. Okay, well, subsequently we defined what we call a regional ionospheric perturbation metric, which is based, we looked at several ways of defining this, but the simplest way turned out to be the best. I'll have a comment for that on that more at the end of the talk. It's defined to be the maximum value of the chi-squared of the fit, or the disturbance metric achieves on the grid. And this is a function of time only, and the storm detectors trip when this metric exceeds a certain threshold for a certain period of time. And I'll discuss that more in a minute. Finally, I want to mention the Ionospheric Disturbance Index, which is simply a scalar associated with a single storm, and it's defined, well, I'll show you the definition of that in a minute. And it's what we use to rank the size of the impact of the storms on WAAS. Okay, so this plot shows the behavior of the ionospheric perturbation metric for a typical moderate storm. Notice that, okay, I've got several thresholds defined here. The first one is the magnitude of the irregularity detector threshold. And I should say that this actually is used in the definition of the Ionospheric Disturbance Index, in that we define this index to be the area under the IPM curve when it exceeds this threshold. This has various nice properties that I discuss in the paper, but time doesn't permit me to go into the details now. But it does. Then one important feature of this index is that it takes into account both the magnitude, or the instantaneous magnitude of the storm, as well as its duration. And it's found, and well, I'll say one more thing about this at the end of the talk. Okay, and then we also had defined, whoops, excuse me. We also defined in this figure the onset threshold and the recovery threshold for the extreme storm detector. I'll say more about that in a minute. In this case, this is not a storm that tripped the extreme storm detector. However, it just barely tripped the moderate storm detector because it got up above the threshold for the moderate storm detector for 10 minutes, which I think is all we require for the moderate storm detector to trip. Okay, so how does the extreme storm detector work? This figure shows how it works. The ionospheric perturbation metric has to exceed a trip threshold for at least an hour. And when it first exceeds the threshold, it enters what we refer to as the, what do I call it, onset confirmation state. Once it's been above that value for an hour, it enters the extreme storm state and remains in the extreme storm state until it drops below the recovery threshold, which we deliberately make lower than the onset threshold, again, to be absolutely sure that it's in a recovery phase and it's headed downward. And it stays in the recovery confirmation state for a lengthy period, and then eventually returns to the normal state. And this was implemented in WAAS in 2007, and it was a huge improvement in the safety of the system. When we define the thresholds for the extreme storm detector, it's important that the detector trip for all extreme storms producing events like the Florida event. But we don't want to set it too conservatively, because what happens when the detector trip is that the whole system becomes unavailable for several hours. I think it's more than 8 hours. And so this is a major loss in availability. And so we have to kind of fine tune it to make sure the thresholds are such that it's safe, but it's not overly conservative. Okay, let me now go to a discussion of what motivated the development of the moderate storm detector. This occurred when we noticed that availability, which is normally, this shows the availability of the system in the first quarter of 2013, and you'll notice that it's basically 100% everywhere except along the coast. And it turns out we were interested in improving the availability on the California coast. And so we had to figure out what was going on here. And what was going on was that we were on a very regular basis, we were getting spikes in the broadcast give that were found to occur just off the coast at IGPs off the coast of California. They occurred twice daily, and they were 2-minute intervals. And so obviously, this is a systematic problem. It's a loss of availability that's an artifact of our methodology. It's not due to anything going on in the ionosphere. And in fact, if you go to the next slide, the spikes were due to basically the contribution the threat model was making when to the give when the geometry of the ray paths was poor. And so up until this point, there was nothing in the threat model that depended on the overall magnitude of ionospheric disturbance. But this motivated, convinces that we actually should introduce such a dependence. And so now we use the moderate storm detector to create a second branch of the threat model. The original threat model has now become what we refer to as the disturbed time branch. And then the moderate storm detector is used to remove threats that occur under moderate storm conditions, and this becomes the quiet time threat model. And we use the quiet time branch whenever when the moderate storm detector has not tripped. Basically, the moderate storm detector works exactly the same way the extreme storm detector works, except that it uses a different set of thresholds that are less restrictive. As long as the moderate storm detector has not tripped, we use the quiet time branch to determine the give values, or the sigma undersampled values that contribute to the give. Okay, excuse me just a second here. Okay, the tripping of the moderate storm detector requires, whoops, I didn't mean to do that. Let's see, here we go. The tripping of the moderate storm detector requires the gives to be calculated using the disturbed time branch of the undersampled. That's what happens well, I just said that. Okay. Without the threats that the moderate storm detector eliminates from the threat model, the quiet time branch of the threat model is much less conservative than the disturbed time branch. Consequently, this improves availability. I just want to emphasize that the consequences of an MSD trip, or moderate storm detector trip, are much less severe than ESD. As I said earlier, the tripping of the extreme storm detector shuts down the system, whereas the tripping of the moderate storm detector effectively just increases the error bars in the uncertainty on the position of the user position estimates. And let me just, this slide shows you the current threat models, and you'll see the quiet time threat model on the left, and the numbers there are much more modest when compared. If you pick out a fit radius and a radius centroid, generally you'll get a number that's, at least in the upper right hand corner, that's smaller than the ones in the upper hand corner in the disturbed model. Okay, I want to conclude my talk now by briefly showing you the how the Ionospheric Disturbance Index ranks the biggest storms that occurred. I should say that if the extreme storm detector had been implemented in 2003, when there would have been 5 storms that it would have tripped in solar cycle 23. I mean, if there would have been 5 storms that tripped, there are actually in solar cycle 24, when it has been implemented, it has yet to be tripped. There were no, from our point of view, there were no extreme storms in solar cycle 24. On the left here, I've shown the behavior of the ionospheric perturbation metric for the April 6, 2000 storm. The figure on the right shows basically the disturbance when it was most intense, as computed by interpolating the values of the delay at the IGPs. And I want to show you one such figure for each of the major storms. This is a major storm. Here's the Bastille Day storm in 2000 was another storm. You can see another the area in red again is basically the metric that's quantifying how big the storm is. The third storm here is the one that I said wasn't really all that extreme. You'll see the area in red is much smaller, but it would qualify due to the conservative nature of our implementation of the storm parameters. Then here's the Halloween storm. I mentioned it was really 2 storms, and on the plot that's going to follow, I've labeled it as 2 storms. And then finally, a month later, or almost a month later, was the final extreme storm. And this one has had a huge impact on the threat model. This was the November 20th storm in 2003. Okay, so essentially my final slide is shows how the Ionospheric Disturbance Index ranks these various storms. And there's one point I want to make. We've calculated in the figure on the left is for the storms in solar cycle 23. The figure on the right is for storms in solar cycle 24. Pay close attention to the fact that the scales are enormously different here. The storms in solar cycle 24, just in general, were much more modest. We had much more activity in solar cycle 23. I think everybody knows that. We haven't actually showed all the storms in solar cycle 23 that were comparable to or greater than the magnitudes of the ones in solar cycle 24. But on the left, I've actually plotted the storm ranking for our two different estimation schemes. The original estimation scheme based on the planar fit and uncorrelated IPPs, and also on our current methodology using Kriging. What's interesting about this is that independent of the different, even though the absolute numbers are different, there's no reason they should be the same. What's important here is the ranking and the order of the storms. And if you look closely, you'll see that the storms the order of the storms is identical. And you may think, well, you know, that should be expected. And indeed it should, in the sense that the estimation scheme shouldn't affect the magnitude of, you know, the ranking of the magnitude of the storms. But this was not the case. And when we looked at a lot of other possible metrics for defining this ranking and getting one that where this behavior was true, that where when changing from one estimation scheme to another, in most of the other cases, it changed the order of the ranking, which was not good. So we consider this IDI, this Ionospheric Disturbance Index, to be fairly robust. And the final comment I want to make is that I wanted to highlight the fact that the storm and the system existed in an extreme storm state. In other words, would have had to have been shut down had the ESD been operating, but the extreme storm state would have been in operation about 0.1% of the time. I know there's some people that would like to get a sense of how frequently is the system going to be down due to an extreme storm. And of course, that's going to depend on the solar cycle. It wasn't down at all last solar cycle. Okay, so let me conclude my talk by summarizing what I've presented. This presentation has described how WAAS protected users in solar cycles 23 and 24 from threats to system accuracy and integrity posed by ionospheric storms. In particular, we've looked at how WAAS monitors the level of ionospheric disturbance, how the mitigation of threats posed by the ionosphere has evolved since 2003, and in particular, focusing on the positive contribution of the extreme storm detector and the moderate storm detector. I think I overlooked one comment. Not only do these detectors make the system safer, but in fact, both of them actually improve the availability, and that's because both of them trip so seldomly. If they tripped more often, that wouldn't be the case. But in fact, the extreme storm detector improves the safety of the system, and both detectors improve availability. And then we've, in our final slide, have shown how the Ionospheric Disturbance Index provides a ranking for the magnitudes of the storms. And my final comment is that I want to highlight the fact that WAAS has not yet ever been found to broadcast hazardously misleading information. This is something we're grateful for, and we're going to try to keep it that way. So I'll conclude on that note and turn back over to Rick. Oh, I want to first, one last thing. I want to thank you for your attention. Thank you.
Great. Thank you so much, Dr. Sparks. This has been a great presentation, and we have solid attendance here today. We do have a few questions for you if you have time.
Sure.
The first question is from Joan Rousseau, who asks, who states that understanding the ionospheric disturbances that impact on the GPS and SBAS components of the WAAS network, can you comment on the impact of a very low power GPS jammer, ground-based 10 milliwatts, on the SBAS and or the WAAS network?
That's not something I've ever thought about. I think I also have online one of my co-authors, Eric Altschuler. Eric, have you thought about that question?
Well, so the ionospheric storm is going to be a more widespread event. The jammer is going to hit really just one station at a time. So our integrity analysis for a jammer, I don't know that we've ever encountered that, but if we were to have a jammer, our integrity analysis supports having bad data from one station, and we are completely safe if we do have that bad data. Now, I don't know that they are really apples to apples comparisons, because the ionosphere is going to be seen by multiple stations over a localized geography. You know, like the threats that Larry was talking about for Halloween 2003. So I don't know that, and I certainly I'm not familiar enough with the jammers to talk units. So 10 milliwatts, I'm not exactly sure.
Okay, well, great, thank you. And also welcome to Dr. Eric Altschuler, one of the co-authors of this paper. And I believe we have additional co-authors in the audience as well. Our next question says, could you use the real-time streaming UNAVCO GPS data with these techniques? Hopefully I'm pronouncing that correctly.
I'm not familiar. I don't know how to answer that question. Eric, you want to take that one too?
I don't think so. WAAS, and again, this goes way back 20 years. We talked about using other external data, and I think there was a requirement that WAAS has a very limited number of input data types that it's allowed to use. And again, I'm not speaking with any kind of authority or knowledge. I just remember, wanting to use things like ionospheric indicators, other types of indicators on how well things are doing. And WAAS really is required to operate kind of in a standalone mode. So I don't think that would fly, although I'm not really qualified to discuss it in any detail.
I should say, by way of introduction, that I deliberately brought Eric along today to answer questions because he's actually involved with WAAS on a much wider scale than I am. So some of these questions that are not directly in my domain of the material that I've talked about most closely today, he's probably going to be much better qualified to answer. He has a much greater knowledge of the system as a whole than I do.
Great. Well, here's a follow-up question from one of the previous attendees. It says, when there is a severe ionospheric disturbance, how does the WAAS compensate for a degraded region, or does it?
For a which region?
A degraded region.
Well, basically the okay. When there is a disturbance in the ionosphere, the first question is it there are two levels of which it provides protection beyond. First of all, if it's not too severe, the ionospheric threat model should provide the protection. In other words, the way the protection is provided is by increasing the magnitude of the error bounds, and basically it'll still allow the user to compute an estimate of their position, but it'll say if there's a disturbance present, it will tell the user effectively that you can't there's more uncertainty in your exact position, and the user has to take that into account. Now, as the disturbances get larger, the first thing that will happen is that you'll trip the local irregularity detector, as I described, and so that and that typically denies well, that prevents the user from using information that's being broadcast in that local region, and chances are that the user may not have sufficient information to determine a correction, but it depends on various factors that I haven't gone into. But and then as the disturbances get larger, well, first of all, eventually you get to the point where you are in an extreme storm and the whole system gets shut down. So their system responds flexibly depending essentially on the magnitude of the disturbance.
Great, thank you. Let's see, the next question says, on slide 32, you show the twin storm of 2003 or Halloween storm. Does the right-hand side plot show the first or second storm?
Oh, good question. Let's see. It's dated, I'm having to look here at my, it says, okay, it's the first storm. Yeah, thank you for that question. I didn't make that. It's the first one.
Okay, great. And there's a, oh, sorry, someone else have a comment?
Yeah, that was a really interesting storm because we saw two similar but different types of behavior. On the first day, we had a very large localized disturbance over California, and then on the second day, we had a very small localized disturbance over Florida. So we call the second day the Florida event, and then that was back on July 18. And that was that very small thing, but it was the same basic behavior where the ionosphere didn't quench in a uniform way. It quenched kind of as a blob, kind of inward versus as a gradient wave across the country. So that was a good, astute question.
Okay, great. And there's a follow-up question on a separate question from a different person regarding this storm event. It says, if a Halloween storm event occurred now, would that mean that the WAAS system would be offline for several hours? Would the outage persistence start at the time of storm 1, or would it be restarted by storm X?
Oh, let's see. Well, I have to look at the figure here. That's a good question. Have we decided if the recovery period is about 8 to 10 hours?
Yeah, the recovery period for
but it would have to be. I don't think it would have recovered. Do you, Eric?
No, I think it did. I think it recovered.
Oh, did it? Well, we didn't have the SD in there at the time. I'm saying, are you saying if the ESD had shut the system down, then it would have been shut down. It would have. Well, you can almost. You can see on the figure on the left where the thresholds are. So certainly for all of this period, it would have been shut. Well, 1 hour after it first crosses the onset threshold, it would have shut down. It would have been shut down for all of this period, plus another 8 hours at least. I guess it might have recovered. It looks like to me it would have recovered briefly before the second storm would have shut it down again.
Yeah, it recovers. I can't hold the cursor, but it recovers 8 hours after it crosses that line right there as it's going.
It would have recovered about there, I guess, if I'm doing this right.
Right. So it recovers for a few hours, and then because of the second storm, we trip again, and then we have to wait and see it through. And I think there's a clearing section. So if you drop down and then go back up, you start that 8 hours again. So you can see it kind of wavering in the first storm, dropping below and above. It's 8 hours from the very last time it crosses, going upward, going downward.
Okay, great, thank you. We do have a question here from Ephraim. He says, can you please review the prediction abilities of ionospheric delays, short terms in minutes or hours, or long-term day?
Well, there's no predictive capability built into WAAS. That ionospheric prediction is a very interesting topic, and there are various ways of approaching that. But predicting ionospheric behavior is very hard because it's so dynamic, and also it's so dependent on external factors like this, you know, if there's a coronal mass ejection impending. I mean, the boundary effect, it's way harder than predicting the weather on Earth. But do you have anything to add, Eric?
Yeah, so it isn't really prediction, but we do have degradation factors that keep you safe over the life of messages. And that is roughly 600 seconds, 10 minutes, something like that. So if you have missed a couple Iono messages in WAAS, you can't keep using Iono, but we will keep you safe from missing one or two. Which that isn't prediction, that's prediction of an error bar or an overbound of an error bar going about 10 minutes into the future. But yeah, we have no hourly, daily, weekly prediction of the delays. But it is a really interesting topic.
Okay, great. Here's another question. How does the storm detector perform over low latitude regions? Is the ionospheric threat model suitable for low latitude ionospheric conditions?
That's an excellent question. That's a really important question. And basically, I think there's a consensus among all of us on the WAAS integrity and performance panel that this algorithm would not work very well as is over at low latitude. At least that's actually a subject of research, because it's much more because of the presence of the equatorial ionization anomaly at low latitudes. The ionosphere presents a much bigger challenge to SBAS or satellite-based augmentation systems. And so you want to add anything, Eric? I mean, you've thought about this a lot too.
Yeah, so as you get, you know, low latitude means, you know, something, it's kind of a shades of gray, right? As you go down lower latitudes, if we had a more sophisticated weighting matrix, different thresholds, things like that, we could probably eke out some performance as you bump up against the equatorial anomaly. Because we use planar fits, we would have a hard time in the middle of the anomaly, like between the two crests. That would be tricky. I think the algorithm would work from an integrity point of view. I think we would be able to generate error bars that would bound delays. I just think from a performance point of view, you wouldn't get very much performance out of it.
Actually, I might have let me see, in my supplemental slides, I think I have a figure that kind of illustrates the problem. Let's see, is this it? Yeah, okay. This is sort of related to the difficulties you encounter at low latitude. What I've done, this is a plot of, I guess it's 16 of the largest storms in solar cycle 24. And what I've done is I've plotted the 100, I've considered at each grid point the 100 largest fit residuals, and I plotted the median value. And what I mean, so that in a sense, I've been trying to get a representative large value, as opposed to, you know, some of these, you might have a single point that was large at each of these IGPs, but I wanted to get a representative value of what the fit residual is at each IGP. And what you'll notice is that, okay, that the biggest values are down here at the lowest these lines are lines of geomagnetic latitude. And so this point is the one that's closest to the geomagnetic equator, and it's showing 5-meter residuals, which is much larger than anything else on the grid. And that's, even though I plotted these data with using storm data, I don't think you're actually seeing the consequences of storms here so much as you're seeing the consequences of the equatorial ionization anomaly. So a structural feature that's there every day. So this is just kind of a little bit of data that shows, and in fact, because of the structure at low latitude, we actually eliminate Pierce points. I didn't have time to talk about this in my talk, but when we do fits, we eliminate Pierce points that for Mexican stations that are looking southward, because we don't really want to include pierce points that are for measurements that are sampling what's sampling going on at low latitude, and for this various reason, because the low latitude presents a problem for our system.
Great, thank you. There is one follow-up question here. Says, I missed the reason for the California off-coast twice daily spikes that necessitated the creation of MSD.
Okay.
Can you explain the cause of those twice daily spikes?
Yeah, it was not ionosphere. It was it was an artifact of our methodology, because what was happening, because we were at the edge of coverage, we were getting ray path. We were in our fits. We were, in fact, let me go back. Maybe let's see if I can find this slide. Hold on just a second. Where is it? I'm not used to using. Yeah. I'll get there in a minute. Just like, here. I don't know. I'm sure there's a faster way to scroll through these. Let's see. Go back to the beginning of my talk. It must be a quicker way. All right, here we go. Okay. Stop. There. Okay, this slide actually is fairly representative of the problem that was occurring off the coast of California, except that it's effectively on the East Coast instead of the West Coast, but it's the same idea. You'll notice that if imagine that we were having the same problem on the East Coast, well, we would have pierce points. Maybe the East Coast would go right through this fit domain, and we would have since all our stations are on land, we would have IPPs that were mostly over land, maybe a few over water, but the centroid radius would have been fairly large. And that's actually the problem. Because we're on the coast, we have a large fit radius, so that causes us to end up sampling. If I go to the typical threat model, if we're up here, sampling this region of the threat model, so we end up, and especially if we have a large fit radius, which we also could have, that could be another result of being at the edge of coverage. So we would be up somewhere in this block, and we would, because of the measurements that are going into the fit, we would be accessing a part of the threat model where the sigma under the term that we add to the give is suddenly jumps up. I mean, there typically are. I mean, you can see here a very sharp gradient in our threat model, something I don't really like, but that's there. I'm guessing that specifically that at the edge of coverage, we're getting twice a day, we're getting ray path geometries that go from, say, this square to sampling this square, and all of a sudden that big jump in the give causes those spikes. And so, as I said, it's basically an artifact of our methodology, but by introducing the moderate storm detector, we can reduce the size of this big brown block, so that when it does jump, it jumps to a value that's not nearly so big, and that's how we get the availability to improve. I hope that makes sense.
Yeah, Larry, just to follow on, when we were developing these 20 years ago, I remember we created video movies of a little black dot moving around over this plot. So you would have a particular radius of your fit, a particular relative centroid of your fit, and the dot would move around. In the middle of the country, the dot was very low in the threat model over the light blues and light greens. Yeah, there. But then toward the outside, toward the edges, it would be up around there. And so the spike has to do with the fact that out on the corner, out on the coast of California, that black dot kind of drifts into that red zone. We get over a 2 meter sigma, which is over a 6 meter give. And then our give jumps from 6 to 15 meters. And then that hurts our availability. That user doesn't have a 6 meter give and it jumps way up. So that's a little more detail on the math behind it.
Great. Well, thank you so much. I think we've used our allotted time today, but I appreciate both of you being here. Dr. Sparks for the presentation and Dr. Altshuler for jumping in and helping with questions. It's been a very well attended and useful webinar for all of us. Has been recorded. We will be posting this on our website within 24 hours. So feel free to come back and view it again and share with colleagues as you see fit. But thank you both. Dr. Sparks, I'll turn over to you if you have any concluding comments.
No, I just, again, want to thank you for extending the invitation. I've enjoyed presenting this material. Eric and I, as you can tell, have been working on this stuff for 20 years, and so it's really fun to get to talk about it.
Well, great. Well, thank you. We'll look forward to having you join us again sometime. But thank you both. Have a great day. And again, we'll have this posted at iowan.org within 24 hours.